We're going to move into a study now of infinite series, and just before we get into that, just some basic definitions. We've talked about sequences, which is a pattern of numbers. If the sequence ends, it's finite. If it goes on endlessly, it's infinite. And then in terms of series, we know that a series is the sum of a sequence. So if we simply add up the terms in the sequence, we get a series. So in my example here, I've got a finite series, and if we've got a finite number of terms, which we can express in sigma notation as you see, we can add up those terms to get the sum of those n terms. So Sn is the sum of a finite series. Now when it comes to adding up an infinite number of terms, we know from our study of geometric series in the past that there may or may not be a sum. So we can't definitively say that our series equals a fixed value. That's in question. So the way we're going to work with this is we're going to define Sn to be the nth partial sum, which means the sum of n terms up to a certain point. The sum of 20 terms, the sum of 21 terms, the sum of 22 terms, the sum of 100 terms. And then we're going to look at a limit of n going to infinity to see if that sum approaches some fixed value. So what we're saying is that by looking at the limit of a finite series as n goes to infinity, or equivalently looking at the sum of n terms as n goes to infinity, if we find that that converges, then we will say that our infinite series converges to a value s. And s is called the sum of the series. If the limit of sum of n terms diverges, then we will say that the infinite series diverges. So that's a lot of theory. Let's try to make that clearer by referring all of that to a situation we know, and that's geometric sequences and series. So let me just take this geometric sequence. We're going to take it to infinity. We know that's this. And I'm also going to represent this in a table format. Term 1, 2, 3, 4, and 5. And we also want to talk about the sum of terms. So first of all, n terms. The sum of the first term would just be 2. The sum of the first two terms, S2, would be 6. The sum of 3 terms would be 14, etc. And then we're going to want to take all this to infinity eventually. Now just as a reminder, remember that we can calculate the sum of n terms for any geometric series the sum of any geometric series is the sum of the terms of the sequence, which are of that form. And the formula for that we've studied in the past is this. So in this situation, the sum of n terms, the sum of any of these could be calculated with a formula. Just applying this formula to our situation, the first term is 2, 1 minus 2 to the n over 1 minus 2, which could be simplified. It's negative 1 on the bottom, negative 2, 1 minus 2 to the n. That's the sum of the finite geometric series. Now, just before I go any further, what I'm going to do is I'm going to represent this table in my calculator. So first of all, let's just enter our original geometric sequence, 2, 4, 8. So if I'm in sequence mode, starting with n minimum is 1, my formula is 2 to the n. Got this set up to graph the first 12 terms or so. And I can see my patterns going up exponentially, which is what a geometric sequence is. Now I also want to represent my partial sums, and this set of numbers here is often called the sequence of partial sums, the sum up to a certain point in the series. So to do that, I'm going to enter a second sequence. And now this one I'm going to enter as a recursive formula, because basically what I want to have happen is to get, for example, S2, this value, I'm going to take the first sum, 2, and I'm going to add on the value of my sequence, 2 to the 2. And to get term 3, I'm going to take the second term, 6, and add on this value, which is 2 to the 3rd, to get that. So my sequence will be, first of all, I'm going to need to specify the first term, which is 2, which I will do so here on the second line. On the first line, I'm going to take the previous term, which is the sequence v at n minus 1, and I'm going to add on the value of my sequence, 2 to the n, at that value. And my first term, we said, was 2. And so now if I graph, what I see in red is a graphical representation of my sequence of partial sums. If I trace, let's trace over to term 4, you'll notice that the value of the original sequence is 16, but the cumulative sum to that point is 30. And if I keep going, I can see that my sum is getting larger and larger. And that's what's going to happen if we talk about extending this series to infinity. What does the sequence of partial sums approach as n gets larger and larger? If you go to table mode, by the way, you can see the values laid out. In blue, the values of the original sequence, and in red is the sequence of partial sums. And the idea now is if we go to infinity, because that's the question we're going to ask ourselves, does my sequence of partial sums approach a fixed value? If it does, we say it converges. If it doesn't, we say it diverges. And it looks like it's getting larger and larger. And of course that makes sense because we're adding on a larger and larger value each time. Alright, so in terms of the big question, does the infinite geometric series converge or diverge? Remember, this is equivalent to asking ourselves, does the limit of the sequence of partial sums diverge or converge? And remember, that formula for this particular sequence was this. So if we evaluate this limit as n goes to infinity, 2 to the infinity goes to infinity, 1 minus infinity is negative infinity, times negative 2 is positive infinity. It diverges. And so if this limit diverges, it means that we say that our infinite series diverges. Alright, I'm going to take another geometric sequence, this time 1/2 to the n, as n goes from 1 to infinity. And so the terms would be 1/2, 1/4, 1/8, 1/16, and so on. I'm also going to represent that in table format. So 0.5, 0.25, 0.125, 0.0625. And I'm also going to show the sum of n terms, which is on its own a sequence of partial sums. Sum of the first term is 0.5. Sum of the first two terms and then of course I'm going to look at this infinitely eventually. Just remember, in terms of calculating Sn, for this particular, if it's finite, then we can use this formula, which is 1/2, 1 minus 1/2 to the n over 1 minus 1/2. And those halves will cancel out. And so we'll be left with 1 minus 1/2 to the n. I'm also going to represent, once again, my table on my calculator. But this time I'm going to set up my table differently instead of using the graphing features. So you'll remember that in the last video we talked about a command called the sequence command. So under ops number 5, sequence, I can simply type in my expression, which is 0.5 to the n, variable n, term 1 to 10, let's say, and let's paste that, and out comes the terms of our sequence, as you can see. Now what I'm going to do is I'm going to transfer this. I don't have to transfer it, I can just look through it the way it is. I can also transfer it to a list, so I'm going to go STO here and into list 1. And if I go over to the stat menu, I'll notice that those numbers are all entered in a column. Now, what I'm going to want to do for S2 is get the sequence of partial sums. So the way I can do that is I can cursor up to L2, and now I'm going to pick a command called Cumulative Sum, which is also under the stat menu, ops number 6, Cumulative Sum, and I'm going to do the cumulative sum of what's in list 1. And what that's going to do is essentially what I was doing in the table here. It's going to take the first term, add the next term in the sequence to get the cumulative sum up to that point. And so you can see all the values that I have here in red being generated in list 2. Which is now great because if I want to extend past S4, S5, S6, I want to take my partial sum, Sn, and take it to infinity. And if I scroll down, I can look at what I think it seems to be approaching, get an intuitive idea as to whether that will converge or diverge. And it looks like it's getting closer and closer to 1. And of course that intuitively makes sense because we're adding on a smaller and smaller number each time. In terms of an algebraic approach, the question I'm asking myself is, does the infinite series converge or diverge? Which, as we said in the theory up front, is equivalent to taking the limit of the nth partial sum, which is this. So if we evaluate this limit, if we take half to the infinity, that's going to go to 0, and so 1 minus 0 would be 1. So it converges to 1, which means our infinite series converges to 1, and the meaning of the 1 is the sum of the series. So we've noticed in our two examples that an infinite geometric series may converge or diverge, and that depends upon whether this limit of partial sums can be evaluated or not. And you'll notice that in the two examples we did, the determining factor as to whether we could evaluate this or not came right at this point, whether this went to 0 or not. And that was essentially determined by the value of r. If our value of r was between -1 and 1, then the series converged, and if that's going to 0, we're left with a over 1 minus r, which is what our series converges to. That's our sum of our series. If our r was anything else, for example, when r was 2, that caused r to the n to go to infinity, meaning that the entire limit diverged, which therefore means our infinite series diverges. So if r, the absolute value of r is greater than or equal to 1, then our series diverges.